everybody. Thank you so much for joining us today. We are so excited to jump into our Wave Physics Fundamentals webinar with you all. As you get settled into the Zoom room, I'd love to encourage you to go ahead and navigate to the bottom of the Zoom window. You'll see a button that kind of looks like a chat bubble. Go ahead and click that. That'll pull up the webinar chat. That is how we will be answering your questions today. So if you have a question at any point during today's webinar, please feel free to pop it in there and we'll try to get that answered for you as soon as possible. To make sure that we don't look like we're talking to ourselves, please set your to section to everyone. That way, when we answer questions, it makes sense what we're saying. Also, other people might be wondering the same thing, so it'll be helpful to them as well. So to get started, go ahead and pull up chat, set that to everyone, and let me know, has spring sprung where you are? It is incredible here in Oregon. There are flowers in every tree. It's absolutely incredible. So let me know, is it beautiful? I have family in Colorado and they tell me there's still snow on the ground. So not spring everywhere. All right, Barbara says it's starting to. Sarah says, yes, 80 degrees. Yeah, it was hot here. And I wore a sweater, which was a choice. Ohio, high 70s. Yep. Oh, upper 20s too. Range. Let's see, pretty here. Pennsylvania. Some flowers are blooming. Very nice. Beautiful in Northwest Montana. So pretty far up there, but it's almost 70. That's great. Sunny and 70 in New York City. First day above 50 degrees in North Vermont, 70 in Kansas. Oh, perfect for an energy mini lab. Lux, I'm very interested in that. Tell us more. 70 degrees in Washington. Oh gosh, 94 in Phoenix. Man, windy in Virginia. Everything is in bloom. I love that. Ooh, Lux shares that the experiment is calculating our power running up the football bleachers. Very cool. Hello, Rebecca. All right, now that I've yapped on long enough, we'll go ahead and get started with the webinar. I have a few housekeeping items to do first. Oh, but it looks like we have someone to say hello.
Oh, yeah. I guess before I share my screen, huh?
Yeah.
Hey. Hi, everyone. I'm Josh.
I'm Dave.
We're going to do most of the talking today. I taught in Virginia, so it's great to see some folks from Roanoke here. I was in Northern Virginia, but Dave taught in Ohio.
I'm also in Oregon.
And in Oregon, yeah.
But yeah, I'm glad to be here joining Josh.
All right. Well, New Hampshire's got whiplash over there. All right.
Perfect. All right, just a few housekeeping items to get out of the way before we hop into our fabulous presentation today. You will receive a recording of today's webinar. It'll be live both on our website and our YouTube channel. It'll just take us about 3 to 5 business days to get that up. That just gives us time to edit and make sure it's looking good before we send it out. You're going to receive an email with that link, as well as a link to today's resource folder. I'm going to drop that link in the chat here as soon as I'm done talking, so keep an eye in the chat for those resources. We'd love to answer your questions during today's session. I see a few raised hands. Go ahead and pop your questions in the chat. That's how we'll answer your questions. And then if we happen to miss your question, please shoot us an email. We are available at physics@vernier.com. All that being said, I'll pass you off to today's presenters. Thank you again for joining us.
All right. So thanks, Dylan. We're going to talk, today's the big rock topic here is about waves and sound, like mechanical waves, that sort of thing. Our goal is to get through 3 activities, standing waves on a string, sound wave in beats, where we'll do a little bit more around that too, using our sound sensor. And then we'll kind of switch gears a little bit and talk about Doppler effect. That actually uses our video analysis app, so it's going to be a little different than you might have expected. Before we get to that, though, I am a little curious. I'd like to know who I'm talking to. So Dylan's going to pop up a quick poll here. I kind of want to know, like, are you already using Vernier equipment in your classroom? If so, like, how comfortable are you with it? And then what do you teach? Do you teach at high school? Do you teach AP at a high school? Are you at a college instructor, a community college, or a four-year college or something like that? It's nice to know these sorts of things just because we can tailor our remarks a little bit to who you are. I guess a little bit of background. I was a high school physics and engineering teacher for 10 years in Northern Virginia, just outside of DC. I taught everything from conceptual physics to AP Physics C. I taught a few years of engineering as well, and I was our school's first robotics mentor, like lead teacher mentor. It was very rewarding. I've been at Vernier for about the last 10 years. I get to work closely with Dave Vernier. He also was a high school physics. Did you teach engineering? Yeah. Just physics? Yeah. Physics teacher. He didn't teach engineering, but he's had some good engineering skills here. And all right, it looks like, all right. It looks like nearly everybody's got used Vernier stuff in the past. If you haven't, that one person that hasn't, all right, welcome. We love having you here. A lot of people are very comfortable with Vernier stuff. I hope that we can show you some things that maybe you haven't seen before. As Dylan mentioned, if you have questions, put them in the chat. If you want a longer, like in-depth discussion, we're happy to give you a phone call or do a Zoom meeting afterwards, kind of talk through some of these bigger questions. And yeah, it looks like we're kind of a mix here between kind of standard first-year physics, AP physics, college physics. All right, I'm going to get into it. I want to talk first about this standing waves on a string activity. This is an activity that's written up in one of our lab books. It's called Advanced Physics Beyond Mechanics. This is kind of like our calculus-based physics lab book outside of mechanics. We have two that's called Advanced Physics Mechanics, and then there's this one that's Beyond Mechanics. Beyond Mechanics includes thermodynamics experiments, waves, and light and sound. It also includes circuits and that sort of thing. If you'd like to see a copy of this particular activity, Dylan shared a link to a Google Drive folder. That Google Drive folder has this particular activity in it. It looks like this. You'll see a folder for the Doppler effect, sound waves, beat tones, standing waves on a string. If you look at standing waves on a string, you'll see there is a student document and then an instructor document. The way this particular activity works is you set up a standing wave on a string. And at first, it's just a standing wave using kind of like a light elastic cord just to get the idea of what a standing wave is. And then students collect a lot of data around this particular setup. We switch from an elastic cord to what I'm using here today is kind of what we'd expect you to do. It's kind of like a heavier braided cord, you know. And the way this experimental setup allows you to easily adjust the total length of the string. It allows you to adjust the tension on the string by changing the hanging mass, how much hanging mass there is. And then using the power amplifier and I'm going to use a LabQuest 3, but we could use like a frequency generator. You can adjust the frequency of the wave that you create on the string as well. I'm going to switch views here so that you can see my setup here. I'm going to drive it a little bit so you can kind of see what that's like. I'm going to, I have that same setup here. And just to identify some of the pieces you see in here, this is the string across. You can see it's kind of hanging over that pulley there. There is a hanging mass off the end of that with about, I think it's got about 100 grams, maybe more like 150 grams on there. This is a speaker. It's a speaker that we sell that's specifically designed to work with our power amplifier. Our power amplifier takes a signal from like a LabQuest or from a frequency generator or some other frequency source and just amplifies it, you know. So you can use it for a demonstration like this to drive this speaker that's how we're going to use it today. But you can also use it to drive like an RC or RLC circuit. That's kind of the most frequent way of using it. I'm going to drive the power amplifier today with a LabQuest 3. You can kind of see it poking out over here. That's kind of hard to read just because to get the lighting the way we want here. So I'm using our LabQuest viewer app here to mirror the screen, my LabQuest screen, so you can see it there. And I've done a little bit of homework. I set this up earlier today and figured out a good resonant frequency for this particular string, for this particular length, and for this particular tension. And I found that at about 53.5 hertz, I get a nice, second harmonic here. You can kind of see, you can hardly see the speaker moving at all, but you get this nice standing wave out of it. As I vary the frequency of the standing wave, you can see it's like that's not quite as good if I drop it down to 50. If I go too high, if I go too far past 53.1/3, I also start to lose it again. This particular app on the LabQuest 3 allows me to easily double or halve the frequency. Just we know you're likely to use it for standing waves and stuff like that here. If I have this, I get back to the fundamental pretty well. That turns out nicely. It's also, I don't know if you can hear it vibrating the table, but this is a lot quieter as well, although it starts wiggling. It's too much vibration apparently. Oh yeah, look at that. And then if I double this, that'll solve the problem. I can also double it again to get the next harmonic, but that also is a little, you can see here that there are places where the string is not moving at all, and it looks fuzzy elsewhere, but I don't know that you can't really pick that up on the camera very well. But that's kind of like what this is. I like this setup because you really can play with all the different components for a standing wave. We know that a standing wave is formed when an incoming wave constructively interferes with kind of like an outgoing wave, a reflected wave, and the speed at which those waves travel depends on the tension on the string and the mass. Well, I guess the mass per unit length of the string. We know that the wavelength, the resonant wavelengths and frequencies depend on this overall length of the string and the speed at which it travels. And so you really can change all those various pieces. And the activity as written, you'll see that students first kind of set up a single standing wave pattern and they compare it. They look at what those harmonics are. They calculate, they measure a frequency and a wavelength. Well, the frequencies they get from the LabQuest, and the wavelength they measure with a meter stick. And then it has them change the tension on the string, and they mass the string to figure out its linear density, and they can vary those things. And like I said, right here, I've only got just this one string, but the accessory speaker actually comes with a braided string like this, and then also a much looser elasticy string that makes bigger waves, so it's a little easier to demonstrate with it. But lots of teachers will swap these strings out. They'll give each lab group a couple of sets of strings and look at how that linear mass density changes the wave speed and therefore the harmonic frequencies and those wavelengths. Am I forgetting anything, Dave?
I think that looks good.
All right.
No questions came up in the chat yet.
All right. I'm going to stop this, and we're going to switch gears here. And Dave's going to talk to you a little bit about sound waves and beats. I'm going to move this over here as well. I guess we can point this towards this. Yeah.
So Josh did a lab using a great lab using the power amplifier, but he didn't use any sensors and he didn't use our graphical analysis program. So I definitely want to do that. I'm going to do a lab from our, he did a lab from an advanced physics book. Mine's from the regular Physics with Vernier book. Let's see, I can hold it up here. show you. Yep. It's a book we written a long time ago, but it's been modified to use new equipment. And even though it's a physics lab, honestly, you could use it at any level of physics. You could even do this exercise with middle school kids, because it's all about learning about sound waves. Now let's see. Josh, are you seeing just my graph?
Yep.
Okay, I'm just going to show the graphical analysis screen. I make the joke that I'm so old, I don't want to have much of me on the screen. Anyway, this is our graphical analysis program, and there's a free version, and it will do this data collection. It'll do every single thing except one little thing I might do at the end. And then there's also a pro version that you can subscribe to. This lab is called Sound Waves and Beats, and it's also about interference of waves. And I think it's a good basic lab that just is a good way to introduce students to sound. I'm going to use, let's see, Josh, are they seeing this? Okay. It's a real simple setup. I decided to show it one time. You can see I've got a electronic keyboard. I've got our Go Direct sound sensor. Go Direct sound sensor. There it is. Go Direct sound sensor, and that's the only equipment. For the record, this lab is the version in the folder that you have was written specifically for using the Go Direct sound sensor and graphical analysis. But you can do the same exact lab using the older Vernier microphone MCA-BTA and plugged into a LabQuest. Now, the version of the instructions will be a tiny bit different, but we have those in our physics book, and if you just tell us you would like them, we'll send them to you. That's a general pattern. We write labs and we write different versions for the different equipment. Okay, now this lab is about sound waves and beats, and of course you need a sound source. As the lab is written, it specifies this keyboard, and the reason is the keyboard can produce really nice sine waves, waveforms that look like sine waves. There's other ways to do it. You might say, well, heck, why don't you just use tuning forks? And the answer is you can do the lab with tuning forks. I've done it many times, but it's a little tricky because you got to hit two tuning forks at the same time. And you got to get sound, and tuning forks die out pretty quickly. So that's another source. And a third possible source would be doing the lab much like Josh did his thing here. Use a LabQuest 2 or a LabQuest 3 or even a LabQuest 1 to produce the sine wave, which it'll do. There's a special app called Audio Function Generator, and it can produce two tones, and you can do beats, and it does a great job. So I'm just sticking with this because that's what the written lab does. I'm going to zoom this out to full screen here again. So one of the great things about graphical analysis with our sensors is if you just start up, usually you start here, and if you just do a new experiment, we sense that there's a microphone connected, and we're set up to do a graph of pressure versus time. Very short time. Notice that only 3/100ths of a second. We call. Josh is changing this a little. Oh, he's making
I'm just gonna make it a little easier for the folks at home
make
to see the axes. and stuff.
Okay, just a scale display thing. Okay, good. I think it's great that it does this all automatically, and we're pretty much ready to go without doing anything. Let me make sure my keyboard's on. I have to turn her on. Probably can hear that, I'm guessing. That's a C on this keyboard, but I set it for the flute sound. Oops, turn off vibrato. It has a vibrato choice. So that's just a C sound. Let me hold that C note and hit the collect button, and look at what you get. Now remember, we call these waveforms. This is a great way to introduce students to what is sound. Well, sound is a variation in pressure. You see the pressure change there. We don't put a scale on this in numerical units. We don't We really don't know what they are, but we know there's a pressure change. And one of the first things you do in this lab is to talk to kids, have kids discover things about terminology like wavelengths, amplitude, and frequency. You might talk about pitch.
You're not hearing me well? I'll move it.
Okay.
That better?
Okay. Anyway, so one of the first things they do is have the kids go through and ask them what is the amplitude of this wave and what's the period, what's the frequency. You might talk to kids about what's pitch mean, or what's pitch mean compared to frequency, stuff like that. Now, this lab, as written, goes one step further. It has the kids actually do a sine wave fit to this. And graphical analysis does that. You just come down here, and you click here, and you choose curve fit. Well, it just did a curve fit. It's kind of a boring curve fit. It's a linear curve fit to all those data. But if I come here, I can click and say sine curve fit, and it does an almost perfect fit. Not quite perfect, but I mean, there's a little glitch there, but I'm glad that's there, because otherwise you wouldn't even know it's a curve fit. But that's a curve fit, and then we can apply this. And then in the lab, they have the kids talk about what does the A parameter have to do with, and what's the B parameter have to do with, and what's the C and D have to do with. Now, if you were a middle school teacher, you could just skip this whole part about the curve fit, but I think just seeing the waveform is a really cool thing, and I'll show some other waveforms later. So that's the first part of the lab, and the second part is really beats. And beats involve two tones being played at the same time. And we're talking about what happens and how we add, and they add destructively and constructively. To do this part, they suggest you go down here, where this is place here in graphical analysis is where you control the time of data collection and the rate of data collection. In the lab, they suggest changing that from 3 100ths to 5 100ths, just so you see a little more of the wave. And notice that it changed that scale a little. Now I'm going to play, that was a C, a high C I play, high on C on this keyboard that I played before. This time I'm going to add the next white key, the D, and hold it and hit collect. And so you get that pattern. I hope you could hear it. You can probably hear beats, right? Listen to the wah, 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 wah. That's what we call beats. But you get this beautiful pattern here. And in the lab, they have the kids, well, first of all, talk about what caused that. Why in the world is this so minimal here and so much bigger here? They talk about beat frequency. And that's kind of a cool concept. So anyway, that's a quick summary of the lab. Remember, the lab's in your handout folder. But there's lots, while you have this set up, there's so many other things you can do. Let me just do file new here to start over, kind of. And students are real, especially, remember, lots of kids are into music, and I can't resist showing differences in waveforms for different instruments. Remember, I'm faking like I've got a flute here, right? That's a flute. What if I change this keyboard? This keyboard will synthesize like a trumpet. Watch the difference for the same musical note. You get a much more complicated waveform. And if you're doing physics, you can go one step further. And this is the only thing I'm doing that requires the pro version of graphical analysis. You can come in here and do an FFT, a fast Fourier transform, which shows the frequency components. And we have actually two other labs that are also, Josh put them in the folder there for me. And one of them is called the mathematics of music. It has the kids work with playing the notes of a musical scale, the first and the root note and the fifth and the fourth and that kind of stuff, and looking at the mathematical relationship with the note between the notes, and they use the FFT to get those frequencies. And the other one is just one called vowel, I think it's tones, vowels, and phones. It's mostly doing the stuff about looking at waveforms. So what have I missed here, Josh? I think that's most of the things So I'll turn it back over to you, I think. What,
Yeah, you wanna, Mustafa is asking about the best way to find the speed of sound using Vernier.
we have, there's lots of ways. We have a lab in this same physics book where we do it with the resonance tubes. I'm pretty sure that's right. And we actually sell a resonance tube now. So I'll check that when I get a chance, but I'm pretty sure that's right. There's other ways with, where you actually pick up a sound from a microphone further away, and that can be done, but I don't think we've written that up.
I think we actually for our the physics projects and explorations book, I think we have one written like
Okay.
that, yeah. Rebecca asked a question about if we have like the older microphone sensor and LabQuest minis, whether it's worth to switch over to Go Direct moving forward. We make right now, we make both what we call our LabQuest sensors. That's like the microphone that Dave showed earlier, and we make our newer Go Direct sensors. This is the older microphone one, right? It's like kind of like a wand style, and the sensing element is right in the tip there. This work does much the same thing. It's got the microphone element is right in there, but because the Go Direct sound has some extra horsepower compared to the microphone, it will also do loudness measured in decibels as well as collect waveforms. Generally these days, we suggest people move, like if they're buying new probes, we suggest Go Direct probes. You'll find that by and large, they cost like the same, maybe a little bit more than the LabQuest sensors, but they're a little more future-proof. And like they do, often you get added features like, you get loudness out of this as well. And if you use our graphical analysis app, it works just as well with the older sensors as it does with the Go Direct sensors. And so you can kind of mix and match as you do. I know it does create a little bit of obviously confusion in the classroom. You might end up with some lab groups with an older sensor and some with a newer sensor, but I think by and large that confusion is mostly limited to the teachers and less to the students. They pick on it.
I'll just add one more thing. The other advantage of the new sensors is that you can use them with iPads and iPhones and Android phones. So that opens up a new door. I mean, for example, you could literally, first of all, remember every person can download graphical analysis for free. So a student could literally download graphical analysis on their cell phone, and you could loan them a micro GDX sound sensor for an evening, and they could do this lab at home.
Yeah. Yeah. I guess along those lines, if you're curious about Graphical Analysis Pro, you want to try it out. In the slides here, I do have a Graphical Analysis Pro license code, license key that you can use until April 28th. You can download Graphical Analysis Basic for free, like Dave mentioned, and then when you first open it up, you can kind of plug in this license key to unlock the Pro features. It is really, graphical analysis is getting better and better, and it really is a wonderful tool. I use it pretty much exclusively now. I want to, there's some conversation in the chat about our speed of sound lab, where you use a tube to measure the round trip time sound of the speed of sound. And I've never seen anybody use Pringle scans before, but I am impressed. That's pretty good.
And someone said they did it today.
I bet. Oh yeah, I bet you could probably find Pringles cans in a high school a lot easier than you could find a 6-foot long PVC pipe. Although if you go to Home Depot and say that you're a physics teacher, they might give you the PVC for free. All right, I guess. Oh, I did want to show. So these slides are in the folder as well, so you can get that key from the Google Drive folder. I also want to show in this Sound Waves, Beats, Tones folder, you'll find the lab instructions and teacher notes for sound waves and beats. That's what Dave showed you. And then these other ones that he mentioned, tones, vowels, and phones, and mathematics of music as well. They all use the microphone or Go Direct Sound. These particular versions are written for Go Direct Sound with our Go Direct or with our graphical analysis app. If you are using LabQuest or Logger Pro and you want these labs written for those platforms, just shoot us an email at physics@vernier.com and we're happy to share those with you. The last activity I want to show you is called Doppler effect. You'll notice that if in the Doppler effect folder, there's some extra stuff in there. There's the lab and the teacher notes, like with the other labs, but there's also a couple of videos. One is a car horn. This is just a video of a car driving by with the horn on so you can hear the Doppler shift. And then the two that are actually used in the lab that you collect data from are these ripple tank waves MP4 video files. So this particular Doppler effect lab uses our video analysis app. We have a version of this written for, obviously, for our older Logger Pro software that had video analysis features built into it. When we started making graphical analysis, we decided that video analysis was such a kind of like a different method of data collection that it really ought to be in its own separate app. So that's become Vernier Video Analysis. You'll see also in these slides here, there is, if you want to try video analysis, there is a license key in the slide as well. I'm actually going to use that one. You'll see that if you click on this link, it's going to actually open the app in a new browser tab. So I'm still in Chrome here. This is a kind of software that we call a progressive web app. It's basically an app that takes the infrastructure of the browser and uses that to kind of to run the app. Vernier Video Analysis has always been a progressive web app like this. It always, you run it within the Chrome browser. If you open up Chrome, a new Chrome tab, and type in graphicalanalysis.app, you'll find that there's also a progressive web app version of that as well. And it just runs within the Chrome browser. If you're on a Chromebook, you have to use the progressive web app version. If you're on a PC or a Mac or some other device, you have the option of using it. I find that sometimes I want 2 copies of graphical analysis open on my MacBook, and I'll pull up the Mac version of graphical analysis and I'll pull up the progressive web app version and I'll collect data in one and I'll create summary data in the other one, sort of thing. So for Vernier Video Analysis runs within the Chrome browser, and what I want to do is I want to open up one of these ripple tank videos. And now that I think about it, I should have done this before, but I'm going to do it right now real quick. I'm going to do this second one because that's the one where it's moving. Or maybe I'll just do both. And in Vernier Video Analysis, what I'm going to do now is I'm going to import that video. And I'm going to find it someplace here. Here we go. And this video is I don't know if you remember the old live photo physics series. They made a whole series of videos. It's an oldie, but a goodie. And it's really a pretty simple thing. You'll see that if you look in the lower left corner here, actually, I'll make this a little bit bigger too. You'll notice that there is a timestamp and a number of frames. There's only 66 frames in the whole thing. If I run it, you can see that this is a ripple tank. They've got the lighting set up really nicely so that as the source moves, I can see the waves propagate easily. The very first slide includes some kind of like some calibration data, so to speak. It tells me that from one side of the video frame to the other side is 26 centimeters. And that's important information to us. Within Vernier Video Analysis, you can collect data from the video itself. I'll show you how that works. But I'm going to first start off by using this kind of calibration data. I'm going to take and go to System. Then I'm going to take this little bar here. And I know that this distance from here to here is 26 centimeters. And so I'm going to say the app tells me that that distance that I've stretched out here is 544 pixels, and I'm going to tell it that is equal to 0.26 meters, 26 centimeters. And when I hit enter, it's going to rescale everything. So now if I ever collect any data, it's going to tell me where that data point was in terms of meters rather than pixels. I'm also going to give it an origin. So I'm going to say, like, right here, where am I at the beginning? Yeah, I'm at the very beginning. I want to say where my wave source started. That is my origin. And so that's 0, 0, and it's going to tell me how many meters to the right and how many meters kind of up the screen my data points are. The last thing I want to point you out here and under this like system information is I can also just kind of measure a distance. Now that I've given it a scale, I can figure out a distance. So in the lab, it has students measure the wavelength, and you can measure the wavelength just by counting a few here. Let's see it. This would be 1 wavelength and 2 wavelengths, 3, 4, 5. Maybe you'd go 5 wavelengths, and that gives you a distance. And then you can divide that by 5 to find a single, the length of a single wave. Because this is the second one with a moving source, you'll notice that the wavelength is different. This was about 4 centimeters or so was a single wavelength. Oh, so the wavelength for kind of in the direction of motion, or I should say ahead of the source. I'm going to do the same thing. I'm going to move this over here, and I'm going to look at 5 wavelengths in the trailing side. There's 1, 2, 3, 4, 5, and it looks like the trailing side 5 wavelengths was about a little less than 7 centimeters. So just by looking at it, you can kind of tell, and this gives you a tool that you could actually measure. In the particular lab, if you look at the lab, the way that they have it there, the way they have that is you follow like you find a frequency by just putting down a single point. I'm going to choose this point right here, and then counting the number of waves that pass in a given amount of time. So if I go back just to where that was, the time is 0, 0, right? I'm just like, I'm at the very beginning of the frame, and I'm going to count maybe how long it takes 5 waves to go past. So I'll just do, there's 1, there's 2, there's 3, there's 4, and there's 5. And I can say that it looks like 0.0175 centimeters or seconds has passed. I've got 5 waves that passed. I can take that 5, divide by that number, and figure out the frequency. And I can do the same on the other side here as well. The lab also has students calculate or figure out the wave speed. I'm going to do that right now. That's pretty straightforward. Now, instead of watching one point and watching the waves go past, I'm going to follow this wave crest. I've intentionally tried to I'm going to zoom in a little bit. I've tried to stay in one point here. You can kind of see it. I'm going to follow this. If I go and I go to the next frame, I want to do this one. If I click on the next spot, in that same spot, it's going to advance the frame. I want to take, here we go. I'm going to say now the wave crest has traveled to here, and now it's here, and now it's here. And I'm just following that wave crest, the kind of the leading edge of that wave crest along. And I'm trying my best to stay in a line, but it's actually okay. As long as I stay with that wave crest, I get some pretty good data. I'm gonna make that a little smaller now so that you can see the graph here. And I'm not so concerned about the towards the top or bottom of the screen motion. So I'm gonna take off the Y here so you can just see the X. And I know that looks pretty linear. And if I do a curve fit, I can get a speed there. It looks like it's about 22 centimeters per second or 23 centimeters per second. And I can do the same thing. I can do the same thing on the other side. One thing that's kind of cool about Vernier Video Analysis is sometimes you have data that is, object moving in a circle, and you want polar coordinates. I can go back to my system information here, and I can change my, I got to X out of this. I can change from Cartesian coordinates to polar coordinates. And when I do, my data table grows quite a bit. And now I get r and theta information, and I get, you know, a radial velocity and an angular velocity as well. So if you really were worried about, if you have students that are worried about getting and following along this axis here when they're trying to measure, you could just have them look at R data, you know. This looks like it's a little truncated. It's only showing 2 significant figures there. So I'm going to change my column options here, and I'm going to make that 3, so it's a little easier to see its motion along the R axis there. One thing you'll notice looking at this, you've got the video here on the left, and on the right I've got this data table and I've got this graph. The data table graph may look familiar because this is like its own version of graphical analysis running within video analysis. You know, so if your students are already using graphical analysis and they start using video analysis, it's going to feel really familiar. It's the same tools, the same graphing, and that sort of thing. Oh, Sarah asked about why I didn't measure the speed of the source. And I certainly could have, Sarah. In this particular place, I wanted to just use that data point that I started with, that I was using to kind of count waves. You could just measure the data source. When you collect data with video analysis, generally you want some nice distinct feature to follow. And you could just follow the very center of the source and move that. Since I had already put one kind of on the edge, that wave crest, I just wanted to use that data point, and so I just continued along with that wave crest. Were there any other questions?
Don't see any coming in yet.
As I mentioned before, in the slides, you'll see there is this there's a trial or a license key for video analysis. You can use this link. You're welcome to use it with your students, and you're welcome to use these instructions and do this lab with your students. You just have to do it before April 28th, because that's when the key expires. All right. I guess I'll mention this Doppler effect video, or the videos and the activity are also come from that Beyond Mechanics book. So the activities that Dave shared with you came from our core Physics with Vernier lab book. And then this standing waves on a string and Doppler effect, they came from that Beyond Mechanics book.
Let's see if we get some more questions. I'll tell a war story while we're while we're waiting. Let me scratch in here.
Yeah. I'll stop sharing.
We developed that microphone, the wand shaped one in the 1980s, and it really was a game changer for science teachers, because the way it was with physics teachers back in the old days was there was only one lab in the whole year that you needed an oscilloscope for. And it was that one I just showed you, because physics teachers love to show those waveforms and, you know, show the difference between this instrument's wave shape and that instrument's wave shape, and what are show beats and all that stuff. You could not do that without a very fast instrument that could graph those things. So one of our driving features in designing hardware in the early days was to crack that thing, because oscilloscopes were expensive. They were a couple $1,000s way back when. So it was a real breakthrough when we could come up with a way to make it so a physics teacher didn't have to buy a stupid oscilloscope for just this one experiment. That's a high school physics teacher I'm talking about mostly. Anyway, just kind of interesting historical thing. Let's see if there's any more questions.
Yeah, Ross mentions that if you use tuning forks, you can have them measure the exact frequency of the tuning fork rather than just the number that's stamped on it. I think that's a great way to kind of help students understand, like, to help them gain some healthy skepticism in the information that's given to them. Jack asked about if you're doing the speed of sound lab where you use the tube and you're measuring the kind of the round trip transit time of a sound wave, what you use for the sound source. If you're doing that round trip sound, we recommend you can just snap your fingers, or if you have like a dog clicker, like you might use to train a dog, you know, those dog clickers. Oh, good, yeah. Jack mentioned there's like echo or resonance, not to confuse things too much, but we have a separate speed of sound apparatus that uses a resonance tube, and it's in a column of water. And in that case, it just uses a standard tone. You know, it's just you play a note. I'll pull that up here real quick. That resonance apparatus, just to be clear what the difference is. There's you know the first one way is to you have a single wave pulse, you know, and you measure the round trip sound, and then the other is to use something like a resonance apparatus, and that's what I'm going to show you right now. This is something we have started carrying just in the last couple of years. It's like 2 tubes, and you fill one, you put water in this tube, and then you put that tube inside of it, and a speaker that mounts on the top of that tube. And so you set up a standing wave between the speaker and the kind of the water level, and you only get resonance at certain points because you know that distance is only certain. And so that's kind of that. I know lots of teachers will do that. Will do this resonance one kind of rather than using a speaker like this, they'll use tuning forks. And rather than using, say, a sound sensor to figure out when it's loudest, where it's resonating the greatest, you're just like using your own ear. But yeah, that works well as too. Kind of 2 different ways of measuring the same thing. Some people really like this. Some people really like using a, you know, the snapping their fingers and looking for that round trip time. Yeah, we get questions every once in a while about measuring the speed of light. And it's tough because light is really, really, really fast. And you got to have some pretty high precision stuff to measure that. Well, I think all that we have left is the giveaway.
Yes, so I have entered everyone's names into a random name selector, and today's winner of a GoDirect sound sensor is Van W. So congratulations, Van. We are very excited to get that going. I'm going to email you right now to get your address. So look out for an email from someone whose email ends with @Vernier, and that'll be me. If you don't see it, check your spam. All right.
All right. Thank you, everyone. It's great to have you. Thanks for all your comments.
All right. Bye, all. Thank you.
Bye.